This video is the first video. It's day one for the first unit of our PhysicsAP course. It's actually chapter 23 in the text. Then it's the unit on geometrical optics. And we're going to be working through this booklet here. It's about 28 pages long. We're not going to do all of them in one day, right? We're going to use this booklet for the entire chapter. I'm just going to spread this out here a little bit where it's a little easier for you to see. Interestingly, we are going to go through quite a few pages today, and we're not even really going to get deep into the material. We're actually going to spend today talking about all the things you need to know before you start. All of the things that your physics teacher kind of thought you knew, right? And thought you were thinking about as well when they were thinking about the problem. And that's actually a real problem in teaching physics, is we often think students are thinking the same things we are, and you may not be. And so I just wanted to use the first few pages to bring you up to speed with what you need to know to do geometrical optics, and then the way that we might be as a teacher looking at the question going, oh, well, let's do it this way because of something that we see. So, some essential pieces of knowledge before we can actually start, before we can dive into working with lenses and mirrors. First thing, when we as physicists, and that's you too, when we describe light in physics, I'm going to say here we use the verb model, and that doesn't mean to model it like a person who models clothing. It means to describe it with like math equations, right? So we can describe light. Okay, using some math equations. We can model it in one of two ways. So there will be times when we're doing some sort of physics experiment, trying to describe how to model it, and we may use one model. It might be the best way to go, and other times we'll use another. And we're bad as teachers for not explaining how you know which model to use. So first of all, let's talk about the models. So one description of light is the wave model. This is actually the model we'll use in the next chapter, not the one we're in, but in the next one. And here we actually say that light is traveling. So here's your light traveling like this. Right? It's not so obvious that that's what's happening, but it is. There's the light making its way across the room, and what's actually happening is you have these waves. It's actually kind of a pair of waves, and so in this little diagram here we've got, going up and down in this drawing, waves of electric field. And at the same time there's a whole nother kind of wave that's happening. And it's actually perpendicular to that electric field, and it's going this way, kind of from side to side in this picture. And that's actually a wave of magnetic field. Now, we don't need to talk about this too much for this chapter, because it's not the model that we're going to use, but just so you know, this is kind of a chicken and the egg story. Which comes first? It turns out that oscillating, waving magnetic field actually creates these waves of electric field. And the waves of electric field create the magnetic field. And so they actually create each other as they wiggle their way across the classroom. And that's the wave model. The other option is to talk about like the particle model. I'm actually going to call it the ray model. So in the ray model, you've actually got these particles of light. Okay, they're actually called photons that are traveling across the room, and they're following a path, a trajectory. And that trajectory that I've got there in the dotted line, that's what we call a ray. So a ray is really nothing more than just a line that the photons follow. It's a trajectory. That's really all it is. And so, okay, let's move on to the next page here. So this is all in your handout. The handout's online too if you needed to download it. So how do we as physicists know when to use each model? Because sometimes the experiments can look awfully similar. And so I've deliberately cooked up a couple of experiments that look almost identical. And I want to show you what I would look at to decide whether I'm going to use the wave model or whether I'm going to use the ray model. So in both of these pictures, I've got a tiny little point source of light, like a tiny, tiny little light bulb. That's what the asterisk is. Okay, so there's my point source of light. And the same thing over here, also have this point source. Just a tiny, tiny little speck of light, so tiny that you can think of it as a point. And on the other side of the classroom, I'm going to have a screen, something that I can see the light land on. Yeah, same thing over here, screen. So these experiments look identical so far. And maybe halfway from the point source to the screen, I'm going to put some sort of object, some sort of mask, some sort of physical thing. And I'm going to look at how that physical thing that's in the way affects the light as it travels to the screen. And maybe I've got a 3-meter distance to the mask and then another 3-meter distance to the screen. Same thing for the ray model. So these are identical, right? There's nothing different about these two stories. Yet the patterns of light that you see on the screen can be incredibly different if you do slight changes to the size of the opening in this mask. So it's possible that you may end up with what we call a diffraction pattern showing up on the screen. You may end up with light smearing out sideways, and you may end up seeing something like this kind of wide little band of light, and it's weird, then there's no light at all, but then a little while later, there's some more light again, and it kind of keeps smearing out sideways. It does it over here as well. And then it goes away a little bit, but then it comes back again. And so we actually see this light from a single opening kind of smearing out and going all over the place on the screen. And that's what we call a diffraction pattern. And that's actually next unit's topic. You know, how that light can smear out. Other times, though, the light goes through that opening in the mask, and it creates this kind of, not a shadow, I guess the opposite of a shadow, right? As the rays from here go and maybe hit just that edge and manage to land there on the screen. And then maybe beside it, maybe this ray goes and hits, oops, kind of jogged that a little bit accidentally, goes and hits here on the screen. And maybe what you end up seeing is kind of just a larger version. I can do a better job of that. Let me try that again. A larger version of that opening. So how do you know which of those two it's going to be? And it all depends on how big this object is that's in the way. If the opening on that mask was something, oh, I don't know, I'm going to make up a number, maybe a centimeter, maybe it's 1 centimeter wide, then I would expect to see the story you've got for the ray model. And in fact, just based on similar triangles, I would expect that this pattern you see of light to probably be 2 centimeters wide, if it's 3 meters and then another 3 meters. But if instead this opening was incredibly thin, incredibly small, maybe, I don't know, I'm going to literally just make up a number, maybe something like 4 times 10 to the negative 5 meters, or what some people might say is 40 micrometers, right? Micro is 10 to the negative 6. So in other words, it's really small here. Then you would get the diffraction pattern. And so as a physicist, we look at this and we go, oh, well, how big is that opening? Oh, it's super small? Oh, you're going to get a diffraction pattern. Or if somebody says, it's a couple centimeters wide. Oh, well, then you're going to get just that geometric pattern you see over on the side. So this is on the right. This is the chapter we're about to do. This is geometrical optics. And it happens when the openings or the lenses or the things that are in the way are much, much bigger than, well, let's just say bigger than the wavelength of light that you're using. If the opening size is down around near the wavelength of light or smaller, then it transitions kind of smoothly, actually, into this diffraction pattern. It's not an abrupt thing that goes from one to the other, but as a physicist, we can look at it and go, hey, 4 times 10 to the negative 5, well, that is small, and you're going to get the pattern. And if it's 1 centimeter, we're going to go, well, no, by our standards, that's actually big, and you won't get the diffraction pattern. So yeah, it's important to know when we can use this ray model, where we can imagine it's just photons traveling along these straight paths, these trajectories called rays. And so for the first chapter we're going to do, it's going to look like the story on the right-hand side. Okay, let's look at 6 things you need to know in order to carefully apply this ray model to describe what's going to happen with lenses. So here are 6 truths that I have to be careful, right? I don't want to just assume you know this. So let's overtly state them, and then we'll be ready to do our work later. One possible piece of essential knowledge is this. Light travels through transparent materials and you're like, yeah, no kidding, I know that, but there's more to say. At different speeds. This doesn't in any way violate special relativity. Special relativity says everybody sees light travel at the same speed in a vacuum. So this isn't a problem with special relativity, but it is a truth. And you can actually calculate how fast the speed of light is going to go in a material by using this equation. The velocity in that material will be the good old usual speed of light, c, divided by some special number that's unique to each material, called the index of refraction. It's kind of a slowdown number. So for example, if you were to take a look at water, if you wanted to know, all right, how fast does light travel through water? Well, the speed would be 3.0 times 10 to the 8, right? That's the c value for light. That's the speed of light in a vacuum. And then you would go and you would look up this index of refraction, this n value for water. And for water, you find it in a table, it ends up being 1.33. And so then you can divide. You can sit there and go, okay, well, you know, what does that work out to? I don't know, let's go and take a look here. So 3 times 10 to the 8 divided by 1.33. Looks like we're talking about around 2.25 or 2.26 times 10 to the 8 meters per second. And so each material has its own index of refraction to talk about how much the light slows down. Second thing, these light beams, these rays, these little paths the photons are going to travel along, the rays do not interact with each other. You don't have to worry about the photons colliding. Not a problem. Piece of knowledge number 3, light rays go straight forever. But that's not the whole story. There's more to say. They go straight forever until they interact with matter. Okay, that sounds like we need to know more information about that. So that's going to be item number 4. I've got these photons following their little trajectories, their rays, their paths. They're supposed to go straight, not interfere with each other, but they may interact with matter. Okay, and I'm going to suggest to you that there are 4 ways, 4 things that can happen here, 4 ways that light can interact with matter. All 4 of these things can be happening in one experiment. And physics teachers, we are so bad for maybe only talking about one at any given time. And students are sitting there going, well, wouldn't this other thing be happening too? And the answer is, yeah, it probably is, but we just didn't want to talk about it. So we have to be careful as teachers to realize that maybe we should be talking about all these things all the time. Could that make it confusing? Maybe, but at least we should be ready to talk about it. So I've got two transparent materials here. I want to make this one over here glass. It has an index of refraction, a slowdown number of typically around 1.5. It can vary depending on the types of glass, but it's around there. And let's make this over here some water. So maybe this is like an aquarium, and you've got some water kind of bumped up against some glass. And so for water, the slowdown number is not as serious. Light does not slow down quite as much in water. Okay, one possibility could be that first little path you see. So here's a photon cruising along, and all of a sudden it does that. Okay, I'll call that option A. So option A, you could get what we call a refraction, which is a bending at a boundary. So when you switch from glass to water, you're definitely going through that boundary line, and that's where you're going to get a bit of a bend. The other option, turns out not every photon would do that. Some of the photons would look at that boundary between glass and water and say, whoa, that's going to behave like a mirror. And you'll actually see a percentage of the photons bounce back, just like a mirror, with the same angle in as the angle that you have out. So we'll call this option B. You could get some reflection at a boundary. Turns out it always does a little bit of both. A certain percentage will refract and go through, and a certain percentage will reflect. More options. Here's a light beam, it did a little bending, but then it comes to some little speck of dust that's maybe floating around in the water, something that's just included there, some inclusion in the water. And you could have option C, where it hits that little speck of dust and just gets absorbed. Just the energy gets converted to heat. So we could have some absorption. In the material. Or maybe it doesn't quite get absorbed. Maybe it actually just hits that little speck of dust, that inclusion, and just kind of ricochets off and bends a little bit. And so that last option there is what we call scattering. And so if there's some dirt that's been included in the glass, kind of got stuck in it when the glass was formed, yeah, then you could get some scattering off of that. I'm not too worried about the absorption and the scattering. I want to focus a little bit more on this bending issue, this refraction, maybe the reflections as well, because we're going to look at lenses, which can do some refracting, and then some mirrors, which are going to do some reflecting, and see how they can affect our geometrical optics. Okay, essential piece of knowledge number 5. We're going to talk a lot about objects, right? So we should define what they actually are. An object is really going to be nothing more than a source of light rays. Oh, and by the way, I'm going to put in here, and lots of them. Billions of them every second. Even that's an underestimate. So what could an object be? It could be a light bulb. Light bulbs definitely have lots of little photons coming off following some rays. And so light bulbs give off their own light once they're hot enough. And so you'd have little trajectories, little photon paths going like this, coming off that filament. So the light bulb being incandescent, being hot enough, it can actually just emit its own light. And so those kind of objects are what we call self-luminous. They're just capable of giving off their own light. But people and roadrunners can't, not at least visible light that we can see. So they have to actually reflect light from things like light bulbs. So I'm going to put in here, others reflect light Well, they're going to reflect light from things like that, right? Like the light bulb. So here's a light bulb right near the Roadrunner, and you might have some light come down and hit the Roadrunner right on its beak, and then it could just go and it could bounce off. Or it might bounce off and go in a different direction as well. The neat thing about most objects is that they're not totally smooth. So if you could actually zoom in on the surface of the Roadrunner's beak, you would notice that it's actually kind of rough, right? It's a little bit fuzzy. It's not perfectly optically smooth. And so when the light comes in from that light bulb, this is actually great news. When a whole bunch of little photons come in here, all following very similar paths, when they go and hit all those rough edges, it's like hitting a whole bunch of little mirrors that are all arranged at different angles. And so the good news is the light rays that come off will go in all these different directions because they hit all these rough surfaces at slightly different angles. And so when they do that, we get this diffuse reflection, right, because of the roughness. So you might hear that phrase, yeah, we've got some diffuse reflection. It's just really saying a rough reflection. The good news, that means that no matter where you're standing, you can actually see the Roadrunner's beak, because the light, even though it might be coming from one light bulb in one corner of the room, it's actually going to bounce every which way. And people with their eyes will be able to see the Roadrunner no matter where they're standing, because the light will get bounced all over the room off the beak. So speaking of using your eyes to see things, here's our last sixth piece of essential knowledge. We're going to talk about, what does it take to see an object? How do I go and look and go, hey, I can see the Roadrunner right over there. The lights are on in the room. Somehow that's going to work so I can see it in my eye. Well, here's what's actually going on. You see an object, you perceive its location when some, maybe not all, but some of the many diverging rays enter your pupil and are focused on the retina. So just looking back at this picture up here, the rays coming off that bird's beak are going every which way. So we would say, yeah, these rays here are diverging, right? They're heading outwards from each other. Well, when they get to your eye, the lens in your eye is going to take those rays that are actually heading away from each other, and it's going to organize them. So let's look at some rays. Some of the rays, unfortunately, when they bounce off the bird's beak, are going to miss your eye entirely. It's kind of sad, but look, there goes one. Okay, we're not going to see them all, right? But as long as my eye has a chance to grab some of these rays, let's watch what happens when a ray comes in like this, little photon path like that, hits the lens of your eye. It's going to do some bending, which we're going to look at on the next page. And the bending of your rays there as it goes through your lens is going to cause them to bend and land right here at this spot on the back of your eyeball. And even other rays that are coming from this bird's beak are going to do the same thing. So a ray coming off that same part of the beak heading this way, if it hits the lens there, it's going to do a nice little set of bends from Snell's law, and it's also going to get arranged. It's going to get focused to that same spot on your retina. And right there on the back of your eye, that whole back surface of your eye, you've got some light-sensitive biology there that's going to say, hey, look, I got some orange light landing on me in this one spot right there. And it's going to send a message off to your brain, because every little spot of your retina is wired kind of individually to your brain. And the light coming off the bird's feet, well, they're going to also, those rays are going to get organized by this lens, and they're going to land at another spot on your retina, a different spot. And even if this ray was to go this way, so it's diverging, right? They're getting farther apart as they leave the toes of the bird until they get to the lens, and the lens is then going to bring them back together. But they were diverging, at least in this zone of the story right here, right? You can see those rays getting farther and farther apart. The good news is your eye can pull them back together and organize them so that the retina can actually see those rays all coming down to one spot. So that's how you see things, is when your eye manages to get them all focused and organized to land on the biology, and all the different parts of your retina, they're all individually wired, those parts, back to your eye. Okay, well, let's talk about kind of the bending that's happening here on that lens. And so to do that, we still haven't even really started this chapter yet, but we're okay, we're right on time here. We're going to take a little review of what we call Snell's law. Okay, so Snell was a physicist, and he actually came up with a neat little equation to talk about how light would bend based on knowing the indices of refraction, those slowdown numbers. So here comes a little ray of light heading towards this glass. I'm going to just make up an angle for the sake of these calculations here. Let's say that if you were to take a protractor and measure the angle of that ray compared to this line right here, that's perpendicular to the surface of the glass. That line's got a special name. It's called a normal line. And in this context, the word normal means perpendicular to. So it's perpendicular to the glass surface. Let's propose that you take a protractor and this angle right here ends up being 50 degrees. Snell's law works like this. He said if you take the index of refraction for one of the materials and then multiply it by the sine of the angle you see for the ray compared to that normal line that I've drawn in red, that will equal the same thing on the other side of the boundary after we go into the glass. So 4 things, as long as you have 3, you can find the 4th. In this particular story, playing around on the air side, air has a slowdown number of about 1, doesn't really slow down at all. And the angle on the air side is 50 degrees compared to the normal. And then on the glass side, I have a 1.5, and then the sine of the angle after it refracts. I'll save you some time. If you solve that, you'll find that it's 31 degrees. And so that tells me that the ray that gets through and refracts is going to be a little closer to this red line. Okay, it's going to be at a 31 degree angle. You know, maybe something kind of like this. Okay, so we have a 31 degree angle in there. Now, physicists, I mentioned this before, physics teachers are so bad for telling you half the story. That's not the only thing that the light will do there. Sure, some of it will refract, but you know what? I got to be honest with you. Some of the light says, no, I don't want to actually go and bend into that material. I'd rather reflect like a mirror. And a little bit would actually get reflected off at a 50 degree angle. But I don't want to talk about that. So I often wouldn't even bother drawing that in. But I got to be honest, it's there. You always get a bit of a mix there between the reflection and the refraction. It doesn't all refract. Okay, well, I might want to go and figure out what's going to happen here when this light ray tries to leave the glass. I would have to draw in a normal line again. And I could either use some geometry skills or I could grab a protractor to measure the angle for that ray compared to that red normal line. It ends up being 59 degrees. And then I could say, oh, okay, let's find the angle on the way out. So we could do Snell's law again. Okay, let's give it a try here. We would be going 1.5, because we're in the glass, times the sine of 59 degrees is equal to 1 when we make it out into the air, and then sine of the angle out in the air. I'll save you a little time. You can try this. If you do that on your calculator, you get one big error. Your calculator just says, hey, I cannot find this angle for you. Its sine value is bigger than 1, can't be done, it's impossible. And that's actually trying to tell you something. it's trying to tell you that this light ray right now is experiencing something that we call TIR, total internal reflection. All of the light this time gets reflected, not a percentage like we saw up here, okay, where when that was happening, a little bit got reflected and a little bit got bent, got refracted. Here, it's total reflection. So even though there's no shiny mirror, it behaves like one, and it will entirely skip off and head in this direction. It'll actually skip off with a 59-degree angle again. 100% reflection in that story. Okay, so that's what that TIR stands for, total internal, total on the inside reflection. Okay, well, I'm going to finish this story off real quick, and then we're going to talk about something called the critical angle. When you get to here, you would draw in a normal line, do a little geometry, and you'd find out that, hey, this is 31 degrees. And then the light on its way out, we can find out its angle here. And if you do Snell's law again, it's actually the same as the top of the page. This would be 50 degrees. And there I go and do it. I didn't want to talk about the fact that, you know what, a little bit of this energy will actually reflect back at a 31-degree angle. But I just wanted to talk about the part that got out. So I might be tempted only to draw that one, leaving at a 50-degree angle. But to be thorough, I should draw that one. And it goes and bounces around some more as well. So that idea of it splitting and some reflecting and some refracting, that's pretty typical unless it's undergoing TIR. And when people are exploring that whole TIR thing, they sometimes want to know, well, like, when do I know that will happen? And it's sometimes useful to find what we call the critical angle. This is the first angle where you're going to get total internal reflection. So I always remember it this way. The critical angle is the angle on the slow side that would be the glass in this story when the fast angle is 90. So in this particular story, if you wanted to try to find the critical angle, you could. You could say, all right, well, I've got the fast side is the air with an index of 1. Let's put a 90-degree angle there. And then on the slow side, we have our 1.5 sine of theta. And when you do that, you'll find that the angle here, the critical angle, is around 42 degrees. So that's the first angle where, when you get there, you're going to get total inside reflection. And 59 is much bigger than 42, so that's why when we had the 59, we were definitely seeing TIR. Had the story been different and this was 58, it'd be TIR. If it was 57, it'd be TIR. If it was 43, it would be TIR. But if it was 41, you'd get the mix, a little bit of reflection and a little bit of refraction. Okay, still not quite ready to start the chapter, but man, are we getting close. What happens when rays of light get to a window? Well, if they happen to hit straight on, like in line with the normal as we would call it, the rays would actually just go perfectly straight through the window. They would slow down in the glass, but they would go perfectly straight through. A more interesting story is, what happens if the ray hits at a nice angle like this? Then what happens? I always think of it as being like a paddle boat that's coming in with paddlers paddling, and they're making their way in towards that slower material. And what you can see is that a paddler over on this corner of the boat is going to get into that light blue slow down area first, and they're going to slow their paddling down. But all the other paddlers, including the one right beside them, would still paddle fast for just a little bit. And that's going to twist your paddle boat or your canoe or whatever it might be. So if you think about it as a little boat with maybe two paddlers side by side in every row, you can look and go, oh, okay, well, that's going to twist the boat while it makes that transition across the boundary. And it's going to then make a path like this. And yeah, there I did it again. There's probably some reflection coming off, but I don't want to talk about that, so I'm not even going to draw it in. But it is there. Okay, so here's my light ray going into the glass. And then it does the bend again. And it's going to actually end up pointing in the same direction it was before it went into the glass. And so when you're looking through a window, not really much happens except the light ray just jogs over to the side slightly, right? Like if you look, there's a little bit of a jog to the side. But it's basically a parallel path to what it was on the way in. So when you look through the window, things are pretty much where you think they are. They might be just slightly to the side, but the jog is less than the thickness of the glass, so not a big change. Windows, not all that impressive to me, but a lens shaped like this, super cool. Let's see what happens if a light ray was to come along and strike the lens maybe up there. If I really wanted to do this correctly, I would have to do Snell's law, and I would draw in a normal line. I'd say, okay, well, there's my perpendicular line. And I would do Snell's law, and I would find that it twists in a little bit, and it might go like this when you do the math. And then when it gets to the other side of the glass, it's not like a window. Here, those normal lines are not pointed the same way, and it does another twist. So it ends up doing a double bend in this story. And it's definitely got some overall bend to it. It's actually a double bend, right? It bends twice. But I got to tell you, we're going to be lazy when we go to do our drawings. And we're going to say, all right, yeah, I don't really have a lot of time to draw that. Can I just draw it like this? And we'll say, yeah, it's going to go in and it's going to bend. And that's how we'll draw it. But it's actually really some laziness that lets us draw it like that, because it actually does two bends. But it definitely does an overall bend, so I guess that's a fair thing to do. Okay? Unlike the window, where overall it doesn't do a bend. And that takes us to the last kind of pair of pages for the day of just getting ready to do geometrical optics, just getting ready to look at lenses. And what we can see is this Snell's law caused this double bending that's actually going to be important. So, what's it going to take to make a neat little picture of this Roadrunner show up? If you were just to take a piece of paper, just some, screen material, like some movie screen material, just paper, and put it there and have a bright light in the room and bring the Roadrunner nearby, you will not get a picture of the Roadrunner on the paper. Here's why. When the light leaves the light bulb and bounces off, say, the beak, some of the light, unfortunately, is just going to go backwards. It's like, oh, that's too bad. But some light will make it to the paper. And some of it might go right kind of here, maybe right where you'd want. But more light from the beak, because it's a rough, diffuse surface, might go and diverge this way and land there. And some of that beak light might go and land here. And yet other beak light rays might go and land there. And if that's not complicated enough, then there's light from the wing. Right, so you've got some wing light that might go and land there. Maybe some more wing light might go and land here. Or maybe some wing light goes and lands right there. And now there's the foot light. Got some toe light that's going to come off and go and land here. Or maybe here. Moral of the story, this is a mess. There's no organized way of getting those rays to land in the right spot on paper. So it really is nothing more than one big mess. And you might think, well, maybe it'll work better if I go with the same experiment with my light bulb shining on the Roadrunner. I've got my piece of paper over here. What if I put a window in? Well, windows are no better because the rays can go through and come out in the same parallel path they were following. If the ray went straight through the window, it won't jog at all. If it goes like this, it might go jog and then come out like that. But it's going to come out parallel. Here's another one that's going to have a little bit of a jog to it, just kind of like that. It's still a mess. it's no better than it was before, right? Here's some wing light coming along, little jog, maybe lands there, more wing light. Still a mess. But let's finish with this. This is really neat. If you, instead of using a window, if you use a lens with this shape, kind of convex lens as we'll call it, the rays are going to do a double bend. And if you carefully craft the curvature of that lens, this is what happens. You would have light bouncing off the beak. Yes, some light's going to go the wrong way. Too bad, so sad. But for any ray of light that hits this lens, maybe I'm going to have a ray go like this. Okay, it does a double bend. It actually does a bend on the way in and a bend on the way out, but I'm lazy, so I'm just going to draw it as a single overall bend. That ray, if it strikes the glass there, would bend in a double bend and actually go and land right there on the paper. If there was another ray that actually went here from the beak, that lens will do a double bend to it. It will steer it until it lands there. Also, right in the same spot on the paper. Even if the ray was to go way down here, double bend, and it's going to land right there on paper. So you get this concentrated deposit of orange beak light landing in that one spot on the paper. The paper will be glowing orange as that orange light lands on the paper and then bounces off in every direction because the paper is rough. The same thing with foot light. You're going to have some foot light that might go here, and then it does a double bend, and it's going to go in this direction until it strikes the paper. Right? That's how it's going to interact with the matter. It'll scatter off the paper. Or maybe some of that toe light goes up here. Right? It's actually going to go all over the place. There are going to be billions of little rays, and they're all going to get organized by that lens. So I think that is super cool, and it's worth a note. So this is cool. The way that works. It's going to make this beautiful little picture landing there on the paper. And so we're going to say, oh, that's awesome. We can actually see it, right? So that thing right there is going to be an image where we actually get to see the Roadrunner. Final thing I'm just going to add to the bottom of this just to finish this lesson off. I guess what we've got here, it's through Snell's law, right? A little double bend because of Snell's law. We're actually seeing the lens organizes all of the rays passing through it. And it redirects each one of them to exactly the right spot on the paper so you can see an image of the bird. Next class, we're going to start to take a look at finding where exactly you need to put that piece of paper. How big will the image be? Will it be right side up, or will it be inverted and flipped around upside down? And all of that stuff is going to start next day. But it's taken us just this day just really to get ready and take a look at this and say, hey, we're going to follow little trajectory paths for these photons. We're not going to worry about waves. And they do this little bend when that light ray interacts with the material, when it does that refraction. It's actually a Snell's law double bend, but we're a bit lazy, so we'll just show them as like single bends happening right in the middle of the lens. And if we get our math right, if we get our geometry right, then we can make these cool images that land on the paper.